Okay, today we're going to start our virtual unit on series and sequences. First, a sequence is just a function whose domain is a set of natural numbers expressed as a sub n rather than f of x, where n is your input and a sub n is your output. We do have explicit formulas, kind of resembling just like an x equals y equals, and recursive formulas using from the time before. So let's just take a look first at an explicit formula. We're looking at problem number 1 over here. So it says that a to the n is equal to 2n plus 1 over 3n. So first thing you're going to do, you're going to let n equal 1. And we're just going to figure out that a sub 1 is equal to 2 times 1 plus 1 over 3 times 1, which gets us to 1. Then we let n equal 2. So a sub 2 is going to be equal to 2 times 2 plus 1 over 3 times 2, and that is going to equal 5/3. And then we find n equals 3. We're just looking for the first 3 terms of the sequence here. So we get a sub 3's equal to 2 times 3 plus 1 all over 3 times 3, and that should get us 7 over 9. Looking at number 2, we have this formula right over here. So if we're going to let n equal 1, then we have b sub 1 is equal to negative 1 to the first power over 2 times 1 minus 1, which gets us negative 1. Then we let n equal 2 for b sub 2. So we have negative 1 squared over 2 times 1 over 2 times 2, 2 times 2 minus 1, and that is going to get us 1/3. Then we're going to let n equal 3. So for b sub 3, we have negative 1 to the third power all over 2 times 3 minus 1, yielding us negative 1/5. You might want to take note of this pattern up here. When you raise a negative 1 to an odd power, it remains negative. Negative 1 to an even power, it becomes positive. That's something that helps us to switch signs as we move through. All right, looking at problem number 3, we let n equal 1. So c sub 1 is going to be negative 1 to the 1 minus 1 all over 2 times 1 plus 1 all over 1 cubed, and that gets us 2. Then we let n equal 2. So we have c sub 2 is going to be, negative 1 to the 2 minus 1 all over 2 times 2 plus 1 all over 2 cubed, and that gets us minus 5 over 8. Lastly, n sub 3, getting us c sub 3. We're going to have negative 1 to the 3 minus 1 all over 2 times 3 plus 1 all over 3 cubed, and that is getting us 7 over 27. So these first 3 problems here are examples of explicit formulas. Number 4, 5, and 6 are going to be done recursively. With a recursive formula, we must give you the first term. You can't do this without the first term being given to you. So if I'm looking for the first 3 terms here, I know that a sub 1 is equal to 5. That was given to us. You'll notice here that the term that we're looking for is based on the previous term. So n is dependent on n minus 1, the term before. So in this case, when I'm looking at a sub 2, that was a 5 over there, we have 4 minus a sub 1, the term before. So that would be 4 minus 5, getting us to negative 1. A sub 3 would be equal to 4 minus a sub 2. So that would be 4 minus negative 1, getting us 5. So again, recursively here, we're looking at the formulas. We are looking to find, we're going to let k equal 0 because everything's based on the term before here. So I know, let's see, a sub 1 is equal to 3. A sub 2 is going to be the same as, 2 times the term before, which is a sub 1 minus 1. So it's going to be 2 times 3 minus 1, getting us a total of 4. A sub 3 is going to be equal to, 2 times a sub 2 minus 1. So it's going to be 2 times 4 minus 1, giving us a total of 6. We can even give you more than just one initial term. In this case, we're looking at both terms initially. So I know that a sub 1 is equal to 1, a sub 2 is also equal to 1. And our formula is telling us that n plus 2 is equal to the 2 previous before. So now I'm looking at a sub 3, and that is going to be a sub 1 plus a sub 2. In this case, that's going to be 1 plus 1, which is equal to 2. If I'm looking for a sub, a sub 4, we're looking for the next 3 terms. That's going to be a sub 2 plus a sub 3. So in this case, we know a sub 2 is 1 plus 2, giving us an answer of 3. The next term here, a sub 5, would be equal to a sub 3 plus a sub 4. So in this case, that's going to be 2 plus 3, giving us a total of 5. This is a very famous sequence where this answer is based on the 2 before, and this is the Fibonacci, I wasn't sure of the spelling there, sequence. We're going to be doing some work with factorials in this unit as well, so we need to kind of discuss what those are. 5 factorial here, that just means we're going to go 5 times 4 times 3 times 2 times 1, and that gets us a total of 120. Some things you do want to remember, just here, 0 factorial is 1, 1 factorial is also 1, so both of those give us a 1. If I'm looking at 6 factorial, it's 6 times 5 times 4 times 3 times 2 times 1. That gives us a total of 720. 9 factorial is going to get big real fast, so 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is a total of 362. 880. We could do some combinations with these. So I'm looking at 5 factorial over 8 factorial. 5 times 4 times 3 times 2 times 1. 8 times 7 times 6 times 5 factorial here. I kind of know here that 5 factorial, this is the same thing as here. These guys will cross out, and we'll wind up with 1 over 336. So remember, we're kind of subtracting 1 each time we do this. So this would look like n plus 2 times n plus 1 times n factorial. All of that is over n factorial. These guys canceled. Just leaving us with this piece here. Foiled out, we'd have n squared plus 3n plus 2. Again, we just kind of want to work through this here. I'm going to start off, I have 16 factorial over 13 factorial, 6 factorial over 8 factorial. So I'm going to start with the 16. So 16 times 15 times 14. And then I'm just going to leave it as 13 factorial because I know I have a 13 factorial down here. Then we're going to start with 8. So it's going to be times 8 times 7 times 6 factorial, of which we have a 6 factorial in the numerator. This will cancel here. These will cancel. And what we wind up with then is 16 times 15 times 14 all over 8 times 7, which gives us a total of 60. Okay, looking on to the second page, we're going to start discussing just kind of writing sequences, some little patterns that we can find. What you got to do is you're going to kind of get a series of numbers here, and you need to figure out what the pattern is. And you want to think about it as, how does 1 become 2? How does 2 become 5? How does 3 become 10? How does 4 become 17? These just get easier with practice. If I'm looking here, I can see between these numbers here, so I'm looking to figure that out. Let's just see if I can figure out any kind of pattern. So I'm looking at +3, and then +5, +7. So I'm noticing I'm adding an extra 2 each time. So that is our pattern there. I can't really get a formula for that one. Over here, I'm just looking to see if I could figure out the patterns. If we're looking at a solid pattern here, so over here what I'm looking at is alternating signs and also perfect squares. So this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So it's also perfect squares. Let's see what we're doing here. Let's look at the formulas here. I'm looking to figure out how 1 is going to become 9, how 2 is going to become -12, how 3 is going to become 15. I do see that these are multiples of 3. I also know that I have alternating signs. So my a sub n is going to be -1 to the n plus 1. Because this is how 1 becomes this, I need it to be a square to make that positive over here. And then it's going to be n plus 2 times 3. And again, with these patterns, guys, you just kind of have to work it through. You'll notice if I let a be 1 and be 1, I put 1 up here, it's going to make this positive. That's going to give me 3 times 3. That's going to get me 9. If I were to let n be 2, that's going to get me a 3 up here, leave me with a negative. 2 plus 2 is 4, times 3 would get us the 12. So you just kind of got to look for the patterns here. The pattern on this one is a sub n is equal to 1 over n times n plus 1. So again, how does 1 become this? How does 2 become this? And that 2 is the n's in these patterns. The last thing we're going to be working with is summation notation here. What we're looking at is this capital letter sigma in Greek. And it usually gives us a number that we're going to run through. We're going to start at 1, end at some number. It will have a pattern that we go to, and then we just add them all up in the end. So let's take a look at this first problem here. I'm looking at the summation of I being 1 to 5 of 2i plus 3. So basically what we're going to do, we're going to say 2 times 1 plus 3. We're going to add that to 2 times 2 plus 3. Add that to 2 times 3 plus 3. Plus 2 times 4 plus 3. Plus, and this will be the last one, 2 times 5 plus 3. Go ahead, we add it all up. We're going to wind up with 5 plus 7 plus 9 plus 11 plus 13, giving us a final total of 45. For number 18, we're going to start with I is equal to 0 to 4. So what we're looking at is 2 times 0 squared plus 2 times 1 squared, 2 times 2 squared, 2 plus 3 squared, and finally, 4, 2 times 4 squared. I did not write that correctly. Hold on, we're too far into the video to repeat. This is going to be 2 times 3 squared plus 2 times 4 squared. What we get is 0 plus 2 plus 8 plus 18 plus 32. Summing them all up, we get a total of 60. You do not have to start with 1 or 0. We could certainly start with 6 and end with 10. What we're going to get here is 36 plus 6 minus 3. That's a total of 39. If we let n equal 7 or k equals 7, we get 49 plus 7 minus 3. That is a total of 53. If we let n equal 8 or k equal 8, we get 64 plus 8 minus 3 for a total of 69. Letting k equal 9, 81 plus 9 minus 3 is a total of 87. Letting k equal 10, we get 100 plus 10 minus 3. And when you sum all these guys up, we wind up at 355. The last problems here, we're just going to give you a series of number, and you need to write it in summation notation. So remember, this is term 1, term 2, term 3. We got to figure out what term this one here is. You'll notice this is 7 times 1, 7 times 2, 7 times 3. This winds up being 7 times 12. So what we're looking for is the summation of i's equal 1 to 12. So I have 12 terms here, and my pattern is going to be 7 times I. Looking here for our summation here, I notice the bottom here is just different powers of 2, 2 squared, to the first power, 2 squared, 2 cubed, to the fourth power. On the top, we're looking at our factorials. So this is going to be a summation, and I do know that 64 is 2 to the 6th power, so it's going to be a summation. Let's use k this time, is equal to 1 to 6. We'll have 6 terms in this pattern. The denominator here was 2 to the n power, and the numerator was n factorial. All right, the last one here, number 22, we're looking at a summation notation. Let's let n this time equal 1. We need to figure out what term we're kind of on. I can see that we are definitely here looking at term 11 from our problem. I need to get the signs to rotate, so that's going to be -1 to the n plus 1. So that's going to help me to get those signs to flip back and forth. And I can see that this is 2/3 being raised to the n power. All right, and with that, we have finished up our first of 4 notes on series and sequences.